Hello everyone, my name is Fredo Bhatti and this is a lecture on decision tree for Data 630. In this lecture we go over the basics of decision trees, how we represent graphically tree representation, the process of constructing trees such as data splitting, some of the imperial measures that are used for splitting the trees, and some issues like avoiding overfitting, and we summarize some of the pros and cons of using decision tree for classification problem. Okay, introduction. Decision tree is a type of non-parametric supervised learning method. In the last lecture, I went over some of the principles of supervised learning, particularly classification. And in module 2, we covered on linear regression. So what non-parametric in this context means is we make less assumption in the underlying model. So if you remember from our linear regression discussion, one of the assumption is the critical assumption is there is a linear relation between the explanatory variables and the target variable, and also we made assumption, which is a critical one, that the errors are normally distributed and non-correlated, right? We don't make such kind of strong assumption for decision trees. Not only decision tree, most modern machine learning type of predictive models, we make less of that kind of assumption. So non-parametric means there is no underlying model like normally distributed and things like that. So the model graphically is represented as a tree. It's a tree structure. I have a slide. I'll go over what that looks like. And so decision tree, typical application of decision is for predicting a target variable. In the context of, now you can apply decision tree for both regression problem as well as classification problem. In the classification problem, obviously the target will be discrete categories. So you apply the decision trees for predicting categories. Now also one advantage of a decision tree is that you can actually extract decision rules from the tree, which makes it easier to communicate the result of a decision tree for decision makers. So the rules is something like the if a bunch of if-then statements. In fact, the default output from R is a text which resembles like if a series of if-then statements, which can be used to generate the graphical decision trees. So here is the representation of decision tree in graphical form. It is represented as inverted tree, where you have the root node at the top of the tree, and the leaf node where the actual decisions are made are at the bottom. Okay. So a part of the construction involves then you have to pick a root node and you split the data set or the observation using that variable that you selected as a root. And when you get, now we will discuss about some of the criteria by which you stop growing the tree, as well as what is involved in selecting a variable for splitting, as well as the threshold value of that variable. We will discuss that in subsequent slides. But here you can see that right at the split, at the first split, you are able to arrive at the leaf node, which enables you to make the category decision or the prediction. Here there is a further splitting going on, so you pick another node and you make another partitioning to arrive at the leaf nodes. And these are splitting nodes because you have to make a decision for the partitioning of the data set, and this is a leaf node. So that's the graphical representation. Again, we will go over some of the underlying technique about selecting variables and selecting thresholds for partitioning. So mathematically, this is how we represent decision trees. So this formula here is a way to calculate the prediction accuracy or the proportion of each region. Here, this box, the graphics here corresponds to the leaf stage of the graphical tree we discussed earlier. So in each region here corresponds to a leaf. Okay, so let's apply this formula to, for instance, one region. How we apply this formula to calculate the proportion of observation that fall into a given region. Let's say this is for two variables. You have as explanatory variable x1 and x2 for determining the outcome of the observation. So let's say in this region, in region 1, we have 10 observation, and this is an application of a binary case where let's say yes or no outcome. So for each observation, we calculate the indicator function. Indicator function is nothing but the mapping of an input into a binary output. One, or if it belongs to one class, it becomes 1. The result of the output of the indicator function will become 1, and if it doesn't belong to that class, it becomes 0. So for a binary case, the indicator function for each variable returns the outcome based on whether that observation belongs to the class of interest or not. And we sum over that observation. Let's say in this case, if we have 10 observation and 8 of the observation fall into the category of interest, then you will have 8 observation because you're summing over the output of the indicator function. Okay, again, this says the x values should be in that region, should qualify. So only the 10 observation will fall in that region based on just the example that we're discussing here. And then you divide it by the total number of observations. So 8 over 10 for our example will give you 80%. So that means the estimated proportion will be 0.8. Now there will be uncertainty in that, because if you have, so the decision for prediction, future prediction, would be if an observation falls in this region in R1 with 8.8 accuracy, you will predict it as that category of interest. So that's how you apply this formula for regression, for decision tree. Now this is a classification application, and the same applies for the most part for regression as well, except that instead of counting the number of observations from a given class, you will be taking the average of the outcome variable or the target variable for determining what will be the value of a new observation. You take the average of the number of observations that fall in that region. But for the most part, the application is the same. So this is a mathematical representation of a decision tree. Okay, though, so moving on to how we actually do the construction. Okay, so in general, we apply 2 steps. One will be the initial construction, and another one is a thing called pruning that I'm not going to spend a lot of time discussing about the pruning, because I have dedicated slides about how pruning is done, except saying that there are 2 types of pruning: pre-pruning and post-pruning. Pre-pruning is part of the learning process. As part of doing the splitting, as part of constructing the tree, you do pre-pruning. And post-pruning involves fully grown the tree and then the post-pruning. Again, I will discuss about the difference between the 2 pruning methods and why we do pruning later. So the initial construction involves selecting variables. So in a typical application of a decision tree, any other classification, you have a vector of variables, right? Explanatory variables. So in the construction of a decision tree, you have to, at every iteration, at every stage of constructing, you have to select. There are 2 decisions involved. One, you have to select the variable that optimizes a given criteria, which we will discuss. And then you select a threshold value for the case of a continuous variable. If the explanatory variable is a continuous variable, then you have to pick a threshold value for the splitting. Okay, so that is one step. And then you do this recursively at every step of the decision tree process. At every node, there are 2 critical decisions that you have to make. You have to select a variable that optimizes a given criteria, which we will discuss, and then you have to pick a threshold value for a continuous variable. If that explanatory variable is a categorical variable, then you have to pick by a class that optimizes that criteria as well. Okay. In some instances, most of the cases, even the continuous variable is converted to a categorical variable for the splitting purpose. And then usually it involves recursive splitting. You have to keep doing this, selecting variable at each stage, and then selecting a threshold value, and then doing further splitting of the data set. So if the data on the branches are the same class, when you arrive at a node where every observation falls into one class, then that's a perfect prediction, and you will stop the further splitting because you have identified the leaf node. Now, in general, we don't do that. That leads to overfitting issue that we will discuss later. But that is how this repeated splitting process works. The recursive partitioning that I discussed earlier is a type of divide and conquer approach, in the sense that at every node selection step, we make data splitting. So we partition the data into subset, and we make the decision based on that subset, individual subsets. Okay. So the goal of splitting the data set or partitioning the observation is to increase the homogeneity, which means using some kind of criteria that I will discuss measures the impurity of the node. Okay, and this partitioning continues until one of these following is satisfied. Either when you don't have variables, no more variables, so that means you have used all the variables for making the splits, and even though you have observation, since you don't have any variables to split on, you stop at that stage. Then the other condition that you can't do further splitting of the data is when you don't have any observation. That means all observation fell into one of the categories or into one of the leaf nodes that you have already built, included in the tree. And another condition where there is no need for further splitting of the tree or growing the tree is even when you have variables and observation, the further splitting is not increasing the homogeneity or is not decreasing the impurity of the node. Then at that point you stop splitting the observation or growing the tree. So now this decision of selecting a variable and selecting a split point is a type of a greedy search. Okay. It's a greedy search in the sense that we make the decision at a step iteration with the information that we have at that particular iteration. Okay, so that decision will only be locally optimal. It might not be, the decision we make at any given iteration might not be globally optimal. That is to say that, for instance, in the next iteration, with additional information that we know that the decision we made in the previous iteration is not globally optimal or is not the best given what we know now, we live with the decision that we made. We don't revisit it. We don't go back and adjust the decision we made. So it is local in the sense it's optimal locally. It is greedy in the sense that it is locally optimal, but that might not be globally optimal. Okay. For growing decision tree, there are different algorithms, but the two common ones that we will discuss in this are information gain from ID3 and C45. That came from computer science domain, and another one is a GINA index that was first introduced by CART algorithm. And there's a simple metric which involves just counting the classification error, but in general that's less used. So we will discuss about information gain and GINA index here. Okay, another important consideration about selecting a variable and selecting a splitting point or splitting threshold is also a function of what kind of variable that we deal with, right? So in any typical supervised learning, you have combination of continuous and categorical variables as explanatory variable. Now, this lecture focuses on a classification application of a decision tree where the outcome is a categorical variable, but you can still have categorical or continuous variables, so a combination of those variables as explanatory variable. So the splitting and the selection is partly dictated by what type of variables that you deal with. So for nominal variables, you can have binary split and multi-way split. Okay, in the binary split, divide into subset using the optimal partition. I haven't formally discussed what the optimal partitioning means in terms of using a quantitative metric that we will discuss. The other one is a multi-class or the multi-way class categorized splitting, which involves as many partitions as distinct categories. If you have three classes or three categories in the variable being considered for splitting, then you will have three-way splitting. If you are splitting on a continuous variable, so the binary split considers all the possible splits, and that involves creating histograms and things like that, and that can be computationally expensive. Or if you have another option is to do a discretization into ordinal categories. Ordinal categories are a type of categories where you have ordered categories, like, for instance, low, medium, high. So there is a logical ordering of the categories. So the splitting can be done using that kind of discretization. Now let's discuss how we measure the quality of partitioning the data at each iteration step. Okay, we discussed earlier there are primarily, at least in this lecture, we will be discussing information gain, which came from computer science, and GENA-index from statistics. More or less, both produce the same result. So what is information? Information gain uses entropy, which is a measure, a statistic, as a measure of uncertainty, how much uncertainty we have in a given variable. Okay, so in the context of using entropy for making a split decision, optimal splitting at each node, the entropy is zero when we have a pure set. Basically, one class has all the observation. So for instance, if we split it into two, a binary split, if all the observation go to one of the subset, that subset will not have any uncertainty, and then the entropy will be the smallest, absolutely zero, right? There is no uncertainty. So mathematically, this is how we calculate entropy. So let's say if we have a binary, the k in here is 2k, a binary category. And we take the proportion of observation, so the number of observation from that class divided by the number of total observation we are splitting times the log of that proportion, and we sum over the different classes. If you have two categories in that class in that variable, then you add those two cases. And then you take the negative of that to correct for the case where the log of a fraction is negative. So we add this negative term here. Okay. In general, typically we take base 2 of the log for the transformation for each category, and historically that came from computer science. Binary level is the base of a binary is what is used. Okay, then how do we actually use information gain to optimally select the variable that increases the homogeneity or decreases the impurity of that node? So again, the split, potentially we split into two, data 1 and data 2. We have D, we are trying to split into D1 and D2 subsets. So we calculate the entropy using the formula we just discussed on the entire data set before the split. Okay. Then we split at a split point, and we calculate the entropy again like this, as a sum of the two entropies for the two subset. We calculate the entropy for one, entropy for two, and then we add it. We also add terms, factors, as a proportion of the each split. For instance, here we count the number of observation from the first split and then divided by the total number of the observation. That will be a factor multiplied from one of the entropy calculation. And similarly, we do the same thing. We count the number of observation from the second split and divided by the total number of observation that we are splitting, and divided by the corresponding entropy. Now we take the difference of that, the difference of the marginal entropy, which is the entropy that we calculated before we split it, and then the entropy after the split. So the value we get as a difference of the two is information gain, which is the amount of uncertainty reduced by the split. Okay, and then we do this for every variable, and we take a variable with the highest information gain, a variable that provides us the most reduction of the uncertainty. Okay, so the combination of variable selection and threshold value selection is determined through in the case of information gain, through information gain. That means, taking the difference between the amount of uncertainty we have before the split and the amount of uncertainty we have after the split. Okay, that is how we determine the optimal variable in the optimal split threshold. Okay, like I said, GNI index is the one that is used by the CART algorithm, which R has implementation as well. So for the most part, they produce the same result. And even mathematically, if you remember from the entropy equation, this one is replaced with it was a log of the fraction here. We take the product of the proportion of that class and the log of it. Here we take the complement of the proportion, and we sum over the number of classes, and that's the GNI index. Here, maybe it's easier to explain here in this graph right here, where you have the red one is entropy, and the GNI index is the blue line. And I'm also showing here misclassification error. It's not commonly used for actually building decision tree, but you can see it can potentially be used as well. So linearly related between the proportion and the impurity measure. So the horizontal scale is the amount of, or the proportion of one category. And this is for a binary application, by the way. So here, when you say 0.5, that means we have equal number of classes observation from both categories. And when we have at the extreme end, that means we have number of observation only from one class. So here, when you have a proportion half, 0.5, you have the utmost entropy as well as GNI index. That is at a point where you have the most uncertainty. It is a random guess. You have equal number of observation from both classes. As you go to the right and to the left, the number of observation from one class or the other dominates. And in fact, as you go to the extreme case, for instance, for when the proportion is 1, that means you have observation only from one of the classes, one of the categories, in the case of two category problems. And at that point, you don't have any uncertainty. You can take any observation and then the outcome will be always known from that class, because all the observation from one category. Okay, so that's how we measure the impurity of the node. So the objective of the splitting is to optimize this measure. That means to minimize the impurity. You want as much as possible the same observation from the same number of classes to fall into that category, into a subset, into the split. That way when you apply the decision tree in the future, and when an observation falls in that leaf, that you have less uncertainty, or you are more confidence in stating that which class that observation is coming from. Okay, so that is how we use metric, like quantity metric, like information gain or GINA index, to measure or to optimally select the variables in the split void as part of constructing the tree. So here's an example. Here's an example for using a weather data set. This is an R. I'm not going through the underlying code. The weather data set, you can load it right from R using one of the packages. And just here is the outcome variable, the target variable. So this has a number of variables. You use those variables to predict whether it's going to rain tomorrow or not. So rain tomorrow is a target variable, and then it's a binary outcome. It says yes or no. Just looking at the observation number of relative frequency of each class, the dominant class is no. So just by, if you, without feeding a model, and if you just make a prediction that it's not going to rain tomorrow, you will be accurate to the same extent as the distribution of the class, which would be 215 over 256, the sum of the two observations, the total number of observations. Now, let's discuss how the things that we looked at earlier, so like selection of the variable, selection of a split point, works in this actual scenario. And like I said before, by default, our output is a text version of the output as well. And basically, you can extract this tree from this text output. Okay. So we have 256 cases. Now, the first thing that we do to determine the root node, we calculate the information gain. This is, by the way, this is a R part implementation in R. There are two main types of, there are many, but primarily two types of algorithm decision algorithm. This is R part, which is a traditional part, and the new one is a conditional tree that I believe what is used in the tutorial exercise. And the main difference, there are other differences like parameters tuning and some of the options that you have in the function code, but the main one is in the difference that the conditional tree, as part of the split, it also calculates statistical significance. It provides a p-value. So that means it makes sure the split, the uncertainty reduction or increase of the homogeneity, whether that is statistically significant or not. So at each split point, it has that p-value. If the p-value is lower, suggests that it's not statistically significant, it doesn't perform the actual splitting. So in that sense, it's better because not only you are making the selection, but you are also determining that the selection is actually statistically significant. But this one is the traditional R part, which does not do the conditional splitting or the statistical significance. Okay, let's go back to what we were discussing. So at this stage, at the first stage, we calculate the information gain or the GINA index for each variable and for different splits. And then we select the variable that maximizes the information gain or minimizes the impurity. And in this case, it was determined that pressure 3 ppm, which is one of the variables in the data, and a threshold value greater than 1012 of this variable value was selected as an optimal variable in an optimal threshold. Okay. So if we select that, so if we partition the data, so some of the one that goes to the left, the number of observations go to the left, will be used to construct the rest of the tree on the left branch. And the other observation that goes to the right based on this value will be used for constructing this branch of the tree. Okay, so pressure, if the pressure 3 ppm greater than or equal to 1012, we will go here in this branch. If the answer is yes to that, conditional to that check. Now, by just doing that, at this point before the split, we have, this is the distribution of the whether it's going to rain tomorrow or no class distribution. 84% of the cases is no, and 16%. So the label here, part of the graphics, shows the dominant label, which is no. And you can read exactly the same thing from here as well, right? The root, you have 256, 41 of the cases is no. 41 of the cases yes. And so now that means, now by doing this split, if you go to the left of this, now we have already increased the information gain or reduced the amount of uncertainty. So here on this node, we were only 84% probability or accuracy, the confidence that any observation that we see tomorrow will be no. But by doing the split now, it has increased to 92%. So our confidence increased as a result of the uncertainty going down. Okay. So again, this being a recursive partitioning, a recursive algorithm. Then we do, using the subset observation in this, we make another selection. So we compare all the observation, all the rest of the variables. We calculate the information gain or the AGI index, whatever you're using, and you select the split point, and happens to be cloud 3 p.m. is a variable that was selected in 7.5 is the threshold value. Okay. So when we use that, we are doing further splitting. Now, in this case, it was terminated here. So this is a leaf node because there is no further splitting. These at the bottom levels are called leaf nodes. That's where we make the decision. And again, the same applies here. So our uncertainty went down. Now we have the distribution is 95 versus 0.05. Okay, 0.95, 0.05. That means there is an increase in our confidence that any observation that falls in this region, in this node, is coming from a class node that it's not going to rain. And obviously the other one goes to here, the same thing. Now the uncertainty is a little higher in this node, but again, compared to here, it is much, much better, the confidence we have in here, or much less uncertainty at this level. The same applies to the right side of the observation. So we use the observation that was split at this point to determine the next best variable and the next best split point. Here, sunshine and a value of 8.1 was selected. Again, the probability of having yes here was 0.60, only 0.16. It has increased now to 0.48. Okay. And if we do applying the same logic, we do the split. The things that go to the left are categorized as no, and the observation that go to the right are categorized as yes. Now at this point we have 74% probability or proportion of number of yes observation here, 0.7, compared to where we started was 0.16, 0.48, 0.47. So the amount of confidence we have in our decision or categorization is going up, and the amount of uncertainty is going down. Okay, so this is a simple example. This is how the tree construction is actually performed in the background. Now, I'm not discussing about the pruning, the post-pruning, the pre-pruning, which is part of the construction, but I will have a section to discuss that, how the pre-pruning and the post-pruning is implemented as part of the constructing the tree. Now, let's move to a common model fitting issue called overfitting. In the previous lecture on model performance, I spent quite a bit of time discussing about overfitting, what overfitting means, what kind of issue it would cause for generalization. So in that sense, overfitting is not unique to decision trees, but decision trees generally tend to suffer quite a bit from overfitting. What is overfitting? Again, to just repeat what I discussed in the previous lecture, it is a condition where the complexity of the model is such that it performs really well on the training sample, but it doesn't generalize well for independent set, a set that did not contribute in the fitting of the model. Okay, so that happens when the algorithm works really hard to identify noise, but not real information in the data, and create a level of complexity to predict or to learn that entry cases, and because that information or that is noise, not real data, it makes the performance of the model worse on future cases. So that is overfitting. So now I discussed some of the approaches and methods that are used as safeguards for overfitting. In decision tree, there are some built-in functions or features called pre-pruning and post-pruning. Both are model complexity reduction approaches. In the case of pre-pruning, you stop constructing of the tree early based on some kind of criteria, some kind of threshold value on one of the metrics used. In the case of post-pruning, you fully grow the tree and perform the pruning based, conditioned on some test on independent set. And I'll go over those two pruning steps. So this graph, we have seen a version of this chart before when we discussed overfitting in model performance. So this is a very general method, having a separate training set and independent set for evaluating the generalization performance of the model. Here we have model complexity in terms of number of nodes. Here the error, the generalization error, classification error, whatever error that you are optimizing or minimizing in fitting the algorithm. So here the red line is a training set, the error as performed on model performance on the training sample. So as you go to the right, as the number of nodes increases, that means that the complexity of the model is going up. It's always the case that the performance of the model on the training gets better. That means the classification error or the error goes down. So it is doing better. But that is not always the case on the training set, on the sample set, on the independent set. Here, as you can see, at some point around, I would say, 50 number of nodes. Beyond that point, even though there is a reduction in the error on the training sample, it stabilizes on the independent set, on the test set. So you're not getting any performance on the generalization. In fact, at some point it starts going up. So here, around 50 nodes, the model starts overfitting. Anything that you do, any complexity you add to the model is not benefiting. Okay, in fact, it's making it worse for the performance of the overall model. Okay, so again, this is a general approach that is used for safeguarding overfitting. Now, going back to the case where the decision pruning is for the decision tree. In the pruning case, you stop constructing the tree early. And now, if you're not conservative for overfitting issue, this is the criteria by which you stop your model, your construction of the tree. You stop if all instances belong to the same class. That means that's fully grown tree. So you wait until all observations fall into a leaf, and that's when you stop the tree. Also, stop all the variable values are the same. If there is no any difference in the metric
performance in the impurity measure between the variables, and then that's a point to stop constructing the tree, growing the tree. But if you are more conservative, if you want to mitigate or avoid overfitting, you would use more restrictive stopping conditions. One of them being number of instances less than some specified. So you will have some specified threshold value, user specified threshold value. Unless you meet that condition, you will not do any further splitting, partition of the data, or adding nodes. The other case is class distribution of instances are independent of the available features. So if that condition, if there is independent condition, such as using the chi-square test, the distribution of the instances and the available feature, and based on that condition, you are applying, you are stopping growing the tree, and then that's more conservative in the interest of avoiding overfitting. And also this, we kind of mentioned this early, if there is no improvement in the impurity measure, significant improvement in the impurity. Remember information gain, for instance, the case of information gain, if there is no enough gain information, which means it's not increasing to the homogeneity of the observation in the split samples, then you would stop growing the tree. So that's pre-pruning. In the case of post-pruning, you actually grow the tree to the full extent by having leaves for each category. Individual single, each observation will fall in separate leaves. Then you start post-pruning. The post-pruning case, so you take a segment of the tree that is a subtree, and you evaluate the rest of the tree on an independent set, on the test set, and you see the performance of the model both with the subtree and without the subtree. If it gets worse on the independent test, even though it might go down, the removal of the subtree might cause an increase in the error on the training. But if you see improvement on the test, that means that segment of the tree, that subtree, must have contributed to the overfitting. So you will replace that subtree by a leaf node. Okay, and so you apply this for different segments of the tree, different subtrees. Anytime you see better performance indication on the independent sample set, you replace with a leaf tree. And another one is model complexity. At this point, I haven't really discussed. In general, this is not unique to decision tree. Again, model complexity is an indication of overfitting in most cases. So, given everything else equal, you tend to, in machine learning in general, simpler models are better, given everything equal. Okay, so complexity, try to minimize the complexity of your model in the interest of safeguarding for overfitting. Okay, some pros and cons, just to summarize, what are some of the benefits of simple decision trees and some of the disadvantages of this technique. One of the pros is computationally cheap to build, and like we discussed, it only involves a selection of variables at each stage, and that will help you partition the data sets recursively, and that tends to be computationally cheap. Again, just given to compared to other learning algorithms, easy for humans to understand, and that's probably the biggest advantage in decision tree. Other learning algorithm, for instance, neural network, which we will cover in the next module, tend to be very complex, black box model, usually called, difficult to interpret for decision makers. While decision tree is actually can be interpreted with a set of if-then statements, it's easy to understand for decision communicating with decision makers. And another advantage of decision trees, it can handle missing values, outliers, and so that means it requires minimal data preparation, unlike some of the technique that, for instance, regression, where we have to replace missing values. Out of the box, a decision tree can handle missing values and also irrelevant variables. Some algorithms are very sensitive to irrelevant features, but decision tree can handle, can ignore the impact of irrelevant features. Downsides: prone to overfitting, although overfitting is not only an issue for decision tree tends to overfit a lot. Bias trees of some class dominant. Again, this is not just unique to decision tree, but decision tree tend to suffer a lot from this as well. If you have a large class imbalance, and it will be biased towards the dominating class. And probably the most important one is stable due to variation in the data. So if you have a large variability in the data, then it becomes unstable. That means if you take multiple samples from that same data, from that same domain, and fit multiple linear decision trees, it's unlikely that you'll find the same result. In some cases, there could be significant difference in the learned models from the same data set, but if you take multiple samples, you tend to get different results. So it's unstable in that sense. And low accuracy. This is also an important aspect, particularly when you go to production environment for mission critical type of machine learning models. And personally, I don't remember a time where I found a simple decision tree as sufficient for model fitting. In general, I use many trees together, and I will have a slide talking about how you use ensemble trees for improving accuracy. Unless very small problem. So the simple decision tree means a single decision tree. It tends to have low accuracy. Okay, now this is I'm using this as a motivation slide. We in data 630 we don't learn. It's not part of the syllabus to cover ensemble trees. It is a more advanced application of decision trees. You will learn that in data 640. Okay, but just for those of you who are interested to pursue, if you want to pursue the application of the advanced application of decision tree, this is a way to go. Combining multiple trees, called ensemble tree. So like I said before, single decision tree is often too simple and too specific. The accuracy or the performance tends to be low. So in ensemble, the general concept of ensemble is multiple weak models working together tend to give you a highly performant model. So weak in the sense models that tend to have low accuracy. Okay, so an analogy in human decision process would be if you have a panel of experts reaching out a consensus on decision making. In general, it is better than a single expert, right? So the decision by a committee might be better result than decision made by a single person. Okay, just loosely. You can compare with that kind of human decision process. So in building a single decision tree, often there is a little difference choosing between alternative variables. So this is a disadvantage of the single decision tree. So what do we do in common ensemble algorithms like boosting, bagging, and random forest? By the way, if you decide to study by your own about ensemble tree method, one that is a very high accuracy and then very popular one is a gradient boosting based decision tree called XGBoost. And it performs amazingly well. I have compared it to for a number of data cases, even with deep neural networks, and then in most cases it performs even better than deep learning. So anyway, what ensemble trees is, you feed multiple models to, that is a decision tree model, on a segment of the data. You take multiple samples, in some cases thousands of samples, and combine. For the case of regression, you take the average of all the decisions, and in the case of classification, you apply a majority vote to make the classification prediction. And again, without getting to the technical details of how it is done, it is really high performing approach for model fitting using decision tree. So when you get a chance, just give it a try. But if you don't have time to study ensemble trees, you will be studying that in data 640. Okay. So this is the end of the lecture on decision trees. You may have some question about some aspect of the decision tree, the different algorithms like RPAR, the conditional tree, and we'll discuss those in class. And also, please watch the lecture on model classification that goes with it, because I didn't cover about how you actually perform the model evaluation on both on the training, on the independence, and compare the result. Okay, thank you for listening.